Okay, so part 4 of 6 here. So Mathematica solve Laplace equation symbolitically. So we have the secant partial of u with respect to x here plus the secant partial of u with respect to y equal to 0. So we let c sub 1 and c sub 2 here constant. So our partial differential equation here. So this one, partial of u with respect to x, the second partial of u with respect to x here, then the second partial of u with respect to y equal to 0 here. So we have the functions here. The function is equal to c sub 1, the constant, times ix plus y plus c sub 2 times negative ix plus y. I here is an imaginary number equal to square root of negative 1. So we are going to solve this. We are going now to solve the partial differential equation here. So we have this plot. We have the x and y here from 0 to 1. So we have the height here as a temperature. For example, then we have also the contour here. So at x equal to 0, so the temperature here equal to 0. At x equal to 1, temperature is also equal to 0. So at y equal to 0, temperature is also equal to 0. At y equal to 1, uh, the temperature is equal to sine pi x. So this we have here in the contour, we have the curve here. You can see this the several curves here. So each curve has the same temperature here. So temperature distributes smoothly, so no interior or heat source, pure Laplace behavior. So for example, here numerical examples here. So temperature at y equal to 0, so temperature equal to 0 at y equal to 1. The temperature is given by 100 sine pi times x. At x equal to 0, temperature here equal to 0. At x equal to 1, temperature is equal to 0. So we have now the temperature. Uh, the solution for this is at the temperature as a function of x and y equal to 100 sine pi x times hyperbolic pi y over uh, sine uh, hyperbolic sine pi here. Then we have the numerical values here. If x equal to 0.5 and y equal to 0.5, the corresponding value for the temperature is 19.9 Celsius. Now, we start with the Laplace equation here. We have the equations. So I've already discussed the solution of the equation here. X double prime over x equal to negative y double prime over y equal to negative lambda. So for the solution to oscillate and x to match the sign pi x boundary condition, we set the constant lambda equal to k squared. So solving for this equation, so the solution here is x of x equal to a cosine kx plus b sine kx. Now we are going to apply the boundary condition here at x equal to 0. So capital letter X here is also equal to 0. Then we finally have here the a equal to 0. So we apply x of 1 here equal to 0. So b sine k equals is also equal to 0. So for non-trivial solution, k must be in pi. Looking at the final result, we see the term as sine pi x, which implies k equal to pi, where m is equal to 1. So the k of x here is equal to b sine pi x. Now solving for the y, so we have this equation. So the solution of this equation is given by this. And apply the boundary condition here if y equals to 0. So this is also equal to 0. So it means that if we substitute here the small y here, so we get c equal to 0. So our solution now is y equal to d hyperbolic sine pi y. So substituting k equal to pi. So we have the um, temperature as a function of x and y is equal to f sine pi x times hyperbolic sine pi y. So we are going to merge the constant here, b and d, into a single constant f. So finding the constant, so this is our equation. Now we apply the condition at the top edge, y equal to 1. So this is equal to 100 d of if y equal to 1 here. So the corresponding function in terms of x is 100 sine pi x. So we have here solving for f. So f now is equal to 100 over hyperbolic sine